Kafka is an increasingly common piece of infrastructure in the modern enterprise. Some teams just use it basically as a dump pipe to get data from point A to point B. Maybe they're moving it from an HTTP intake to their data warehouse. Other teams are building, real event-driven microservices applications. But regardless of how you use Kafka, it gets super expensive at scale. Some of these costs are really obvious and direct, like the cost of VMs and EBS. But there are other costs that are a little bit more subtle, like the cost of interzone networking and the cost of your team's time doing operations against a self-hosted Apache Kafka cluster. So let's look at a simplified architecture diagram for open source Kafka so that I can kind of go over where all these costs are coming from. We have a producer that's sending data to some consumers through Kafka. The producer sends that data to the leader broker for the partition it's writing to, and that leader broker replicates to two followers in other availability zones. In AWS and GCP, and soon Azure, if they haven't done it already, they charge you to send data across availability zones. There's a feature called fetch from follower in open source Kafka that lets you read your consumer to read from any of the replica brokers as long as it's sufficiently up to date. That saves you a little bit of this cross-AZ bandwidth instead of reading from the broker across zone. But in the ideal scenario there, it's if you add that all up, it's 5.3 cents per gigabyte transferred through the cluster. These brokers are also stateful. They've got local disks, and you have to do some careful operations to avoid disrupting the cluster when you want to scale up or scale down or replace an instance, as well as if you have imbalanced data in between the brokers. Moving them around also requires manual operations. So the first and most obvious cost is storage. Cloud disks are super expensive. There's really no way around that. There's an emerging pattern that I've seen where people kind of treat Kafka as a data lake and they just never delete stuff. And that pattern can result in a huge explosion of costs when you're using open source Kafka because it's triply replicating the data onto expensive SSDs. Some workloads can handle running Kafka on spinning disks, but then you have to carefully choose how much RAM for the page cache, so that's a bit tough to make work in practice. S3, on the other hand, is way cheaper per gigabyte and seems like it would be an obvious solution to this problem. But regardless of whether you choose EBS SSDs, EBS hard drives, or instance storage, S3 is going to come out much cheaper in comparison, and it has much better durability out of the box than any of those other storage solutions. So that's it, right? I'm just going to end the talk here, and we'll just copy the data to S3, and then our life will be much easier, right? So tiered storage definitely helps. The Kafka community, the open source Kafka community is just now getting tiered storage in the open source product. It's in beta right now. The TLDR of tiered storage is basically the broker copies old data to S3 to reduce costs. A few other vendors have had tiered storage for a while, but it's just now coming to the open source. This definitely helps on the operations side a bit as well, but it's still, the brokers are still stateful and you have to do careful operations the same way you did before. It just makes the local state on the broker a bit smaller. There are still leaders for individual topic partitions, so the manual operations are all still there. And rebalancing data, now you don't necessarily need to rebalance the storage, but if you have an imbalance in your workload between how much data is being written to each topic partition, is still a problem, even with tiered storage. So what if we could get all the way to stateless, where we have no local disks? That would be obviously better. What if we just use S3 for all the data all the time? That's basically the idea with WarpStream. So it's a drop-in protocol compatible for replacement for Apache Kafka that stores data only in S3. And doing this solves two of the major problems with open source Kafka at the same time, which are the costs and the operations. We basically thought that if you're paying a huge tax to run your workload in the cloud, you should at least be able to take advantage of what the cloud has to offer in terms of the great primitives like object storage. So why get rid of the disks? The first problem is just it makes the operations much easier. When you're using open source Kafka, you are destined to treat the brokers essentially as pets and not cattle like you do with all of your other services. You need to constantly be thinking about the life cycle of the broker to avoid causing downtime or data loss. And that process of rebalancing data for imbalanced topic partitions or imbalanced brokers, you need a third-party tool for that as well. The CPU and memory usage of the brokers, balancing that is not nearly as much of a concern. It's pretty uncommon to run into those issues, but it can still happen sometimes with open source Kafka. S3 takes away basically all of this burden that I just described because they internally handle replication, dealing with failures, and all of that stuff. So this is arguably a much more important reason for dropping the disks, which is that when you're pushing hundreds of megabytes a second through open source Kafka and you're paying retail AWS prices, 80% of the TCO of that workload is going to be interzone networking. Like in the ideal situation I described before, where all the consumers are using fetch from follower, it's 5.3 cents per gigabyte that you send through Kafka. And it sounds a little crazy, but that's like the same cost as storing that data in S3 for 2 months. So something is way out of balance there. And with S3, you don't pay for interzone networking. So it's, that cost essentially just goes to zero if you use S3 for all your storage. So how does this work? Presumably somebody would have done this already if it was really simple. And the answer is magic, obviously, but today I'm going to explain a little bit of the magic behind WarpStream. So this architecture diagram of WarpStream is structured to be comparable to the Kafka architecture diagram I showed earlier, but instead of the stateful brokers, in red here we have our stateless agents. They're essentially like a virtual broker. And when I say that they're stateless, I mean you could go delete all the VMs that are running in this workload and you wouldn't lose any data. So they're essentially a thick proxy that speaks the Kafka protocol to clients, but writes data to S3 on the back end. So in our control plane that I have labeled up there as WarpStream Cloud does round-robin load balancing across all your clients for you, so that imbalance thing I described earlier is not an issue anymore. We've enhanced the Kafka service discovery system so that everything in WarpStream works like fetch from follower. Your produce and consume ends up going to a broker that's in the same availability zone as you, an agent in the same availability zone as you, which means you don't pay any interzone networking fees from your client to the agent, and you don't pay any interzone networking fees when the agent eventually writes a file to S3. This basically means that we're using S3 as both the storage layer and the network layer. So when the producer that's in zone A writes to the agent in zone A, when this consumer over here in zone C wants to read that same data, it's going through object storage. It's not like reading it across zones. So there's no interzone networking fees anywhere here. So I need to digress for a moment and describe like the unit economics of object storage, basically. I don't think these numbers probably mean a lot to you out of context, but suffice it to say that writing and reading from S3, it matters a lot how many times you do it for the overall cost model of the system. So what if we've just replaced all the cross-AZ bandwidth fees with object storage fees? That would be pretty terrible. So now I'm going to explain how we avoid that and built a storage engine that's like natively designed for S3. So the first step of that process is to break away from an implementation detail of Kafka where the Kafka broker stores all the data for each topic partition in a file that's dedicated only to that topic partition. In object storage, this just wouldn't work. We flush files to object storage in WarpStream every 250 milliseconds by default to provide reasonable latency. If you did that by splitting the files out per topic partition, that would be roughly $50 a month input costs per partition, which is obviously not sustainable if you have hundreds or thousands of those in your workload. So an important detail of S3's pricing model is that while the operations are relatively expensive, you're not charged for cross-AZ bandwidth when you're doing those, which I've mentioned before. But also, you're not charged for an implication of that is basically you're not charged for the throughput that each operation is doing. So you should ideally try to drive as much throughput through each API operation as possible by doing as much useful work within the context of each operation. And when you combine this with the fact that S3 storage is so cheap, the trade-offs you would make from an algorithm's perspective are a bit different. You would probably prefer to trade a little bit more space amplification to do fewer get or put operations, especially if that's just temporary and you can go clean up the objects later, because S3 is effectively infinite storage. So instead of writing files that are per topic partition in WarpStream, we group files or group records from all the topic partitions into together into one file. So we do this by default every 250 milliseconds or every 8 megabytes of data, whichever comes first. And that means instead of the $50 a month per partition that I described before, it's about $50 a month inputs per agent, which you only run a few of those in under normal circumstances. That's a much more sustainable cost, and it lets us basically decouple the number of partitions that are in the workload from the cost of the workload. So the way that works inside the agent works a little bit like this. The producer is sending data to an agent. The agent buffers it and compresses it and then flushes a file to object storage. Separately, the metadata for that file is committed to our metadata store. And to make the latency of this acceptable, we flush a lot of files in parallel. So if you have a super high throughput workload, we're flushing files to object storage in parallel, but we commit the presence of those files serially to the metadata store to preserve the Kafka ordering semantics. So basically the thing that I described is like we're separating the metadata from the data in the cluster. And the way that we do that and then keep all of the Kafka ordering guarantees is essentially our metadata store is acting as the leader for all of those topic partitions. So while we're flushing files to object storage, we don't know what the offsets of those records will eventually be later. That's done inside the metadata store. This is also a convenient place for us to implement features like idempotent producer, which basically the Kafka client assigns a sequence number to every record, and then if you retransmit that record, it can be deduplicated from records that you sent in the past. So once all of this stuff finally happens, we acknowledge the produce request back to the client with the offsets for the records that it wrote. This means that thankfully the job that the metadata store has to do is fairly small because it's just keeping track of essentially pointers to files in object storage and ordering them. So some of you have probably noticed a problem here, which is that we're flushing a lot of really small files to object storage, especially if we're round robin load balancing your clients and spraying all the records for all the topic partitions everywhere. We've kind of made a problem for ourselves in that when you want to go read that data later, you might be reading only a tiny chunk from every object. So to fix that, the agents in each availability zone cluster with each other, and using a consistent hash ring, we route read requests for pieces of the file to a single agent that's responsible for caching it in memory. We deduplicate concurrent fetches. Like here, I'll describe this like sequence of things that's happening here. In this example, the blue, which is on the far left, that fetch kicks off the aligned 4 megabyte read to storage. The orange fetch arrives later, but before that aligned 4 megabyte read has finished, and we deduplicate that request, so we only do one get against object storage. And this green request arrives even later after the object is in the cache, so we can serve it directly from memory without waiting. And this technique is super effective, and empirically we've seen in benchmarks and in our customer environments that you're doing roughly one get per 4 megabytes of data per availability zone that you're running the cluster in, which is pretty cost effective. So, but what if you're reading old data that's no longer in the cache? What do you do in that case? This is pretty common in Kafka. People like reset the consumer group offsets back to some prior point in time because they have a bug that they want to fix in their application by reprocessing some of the old data. That issue basically brings us to the last step of the process in the WarpStream storage engine, which is compaction. You can see on the left here, there's a lagging consumer 4, that wouldn't have any opportunity, like the live consumers, to share I/O against S3. So what we do to fix that is basically we take all these little files and compact them into big files, so that when you're coming back later, you have data locality on the per topic partition level. We leave the old files in object storage for a while so that concurrent reads can complete, but we clean them up a few hours later. So this is an overview of what that compaction process looks like. We're basically taking distinct batches from each topic partition and merging them together into one big batch so that you can get better compression ratio. And when you're reading from object storage, you're potentially reading a chunk that's like a few dozen megabytes from one topic partition instead of a few dozen kilobytes. So with compacted topics that are a feature of Kafka, this kind of amps up the challenge a little bit for us. Kafka compacted topics are like a completely different feature than the compaction that I just talked about. It's like a feature of Kafka that, because you're writing each record with a key, sometimes applications send data to Kafka that represents like the current state of an object, and you don't need all the prior versions of that object. So you could delete them and pay less for storage and have your application, if it needed to reprocess everything, it would go a bit faster. So that's basically what compacted topics do, is they scan the whole history and they delete the duplicated records. How would we do that in WarpStream? Ideally, you want a data structure that looks something like this. These numbers came from the previous slide, basically. You want a data structure that looks like this, where you have a map from each key to the latest offset that key appears at within the topic partition, because this happens at a per topic partition level, not globally. So the reason why we suspected that this would be hard for us is that in open source Kafka, the tiered storage implementation doesn't support compacted topics. And most of the implementations of compacted topics across different vendors don't support implementations of tiered storage, and other vendors don't support compacted topics. Or if they do, they didn't until very recently. But we already had compaction internally with WarpStream, so we thought, how hard could it possibly be to implement this? And if you have a very low cardinality set of keys in your application, it's actually pretty easy. You could just scan the topic partition, buffer all the records in memory, and do a final deduplication step once you've stored everything in memory. You could, when you encountered a duplicate key, you could just delete the old one as you're scanning. It would be pretty cheap. even if the records are very far apart in offset space, because as you're iterating over this low cardinality set of keys, the active set would be pretty small. But that's not reality. Workloads are not all composed of low cardinality keys. In theory, an append-only set of keys is a perfectly valid use case for a compacted topic. I don't know why somebody would, but it is supposed to work. So we need to somehow overcome the fact that two records can be really close to each other in offset space, but very far apart in key space. And that would make them very hard to deduplicate. If we had to store both the keys and the values for this process, it would be extremely expensive because you'd be growing this map forever. So our solution takes advantage of how S3 works, again, to implement this process entirely streaming, but we do it in 2 passes over the files at the same time. And this is okay because, again, as I said, one S3 get, you can read as much data as you want, essentially, as long as you're okay with the single stream throughput of about 100 megabytes a second. This is basically already how compaction works in WarpStream today. We stream in the input files and we write out the output files. So we're doubling the number of GET requests to do this compaction, but GET requests are already such a tiny fraction of the cost of the workload that it doesn't matter. Serving those live reads is where most of the cost of the GETs come from. So to get started, we open 2 parallel streams to the same file, starting at the same topic partition. And in phase 1, which there's an error on this next slide. The arrow that should be advanced is the green arrow, not the blue arrow to match the phase 1 and phase 2 diagram on the last file or on the last slide. But basically, we scan once and build a map of just the keys to the latest offset, and the second phase follows behind. The second scan follows behind, and we use that map that we generated in the prior step to throw away all the old records. So we can process an entire topic partition and then throw away that map, just reuse the memory for it so that we can process the next partition. And that's basically it. So we just make two passes over the data, and instead of needing to store all of the records for all the topic partitions in memory, we just have the offsets and the keys from each record. So this is what you get from all of that work that I just described. You get a dramatic reduction in infrastructure cost. This is a fairly large workload that we're modeling here, very similar to the workload that we're showing off in the demo at our booth. It's a gigabyte per second of ingress, and this would cost around $1.7 million a year in interzone networking fees if you're paying AWS retail prices, and we replace that with about $60,000 a year of object storage fees in WarpStream, again, all at retail prices. So we've saved a lot of money, and the system's a lot easier to operate. So what's the catch? It's basically latency. The end-to-end latency of WarpStream is acceptable for most applications that we've come across, with very few exceptions. And because a common use case for Kafka is essentially to temporarily buffer data before you move it to somewhere else, this 1.5 seconds of latency at the P99 is just insignificant. But if you do want lower latency, WarpStream supports S3 Express one zone, which is essentially a tier of object storage that's backed by much faster, probably SSDs inside Amazon. And as the name implies, S3 Express one zone is a zonal service. So what we do to provide regional high availability is we write to a quorum of 2 out of 3 of those S3 Express one zone buckets. The cool part is that we also then later move the data to S3 standard, so you pay much lower storage price. You don't have to pay the triply replicated 15 cents per gigabyte per month or whatever that S3 Express one zone charges. It's just the same low prices S3 standard. So now I'm going to show off our, I think you've all seen it. I think almost all of you have been to the booth, but for the few of you that haven't, we have a live workload running in our production account right now. And I'm going to show it to you and describe what's going on. All right. Okay, let's see if I can actually get it over here. There we go. So this is a Datadog dashboard showing off the open messaging benchmark that we're running. It's a standard benchmark for streaming systems, not just Kafka, protocol compatible ones. There's you can use it for a variety of systems. And basically what we're doing here, let me filter this down a little bit so we don't get a bunch of other stuff included. What we're doing here is we're writing a gigabyte per second and reading it 3 times. So it's 1 gigabyte per second in, 3 gigabytes per second out. And while the workload is running, every 5 minutes we're adding and removing a third of the cluster capacity of agents. And you can see the CPU usage go up on the other agents. I think these have 16 cores. So we're definitely approaching the capacity of these nodes, but the overall the cluster just keeps working. You don't really need to do anything. It's about as hard to run as a stateless web server like Nginx. You could go in and delete all these instances at once, and you wouldn't lose any data. I know Kafka is not super exciting to demo, but but this is what we got. I thought you would just like the big number, basically, and showing off how easy it is to scale in and out.